Okay, so everybody do this, okay? Everybody. Yeah, everybody stand up, walk around in front of where you are and sit down on the desk. Or on a different desk, it doesn't really matter. Should everybody sit on a desk? Okay. You need to sit all the way up with your feet off the ground. Okay, good, good. Okay. When I say sensory, what pops into your head? This is the fun part about having all the tests. There's like 7 Olivias in class. So I can just say something. I can just be like, when I say sensory, one of the Olivias, what pops into your head? Senses. What is a sense? Information that I take in. Okay, that's very reasonable. Are you all sensing something right now as you're sitting there? What are you sensing?
How cold the desk is?
How cold the desk is, okay? Right? Put your arm up over your head. How do you know that your arm is over your head?
I can kind of like feel my shoulder and bottom.
Okay, how do you feel your shoulder?
The information, the sensory neurons and information that makes sense in the brain.
Okay, close your eyes. Right, now lean to your left gently. Come back to the middle. Okay, you still know where you are? You sure? Okay, your eyes are closed. Where am I? Can you all tell as you're doing this while you're holding up? Am I moving?
Yeah, 10 o'clock.
10 o'clock? Right over here? Over here? Am I moving again? How do you know that? My voice is moving?
Your feet.
And my feet? Okay, all right, good. All right, now, hands down, eyes open. Okay? Where are you getting that sensory information? How do you hear things? Vibrations, okay. How do you see things? Well, can you all see me? You don't want to see me, but can you see me? How do you see? Eyeball, okay, that's fine. What's going on?
I guess like for like that being sense of neuron involved, the cornea, right?
What color shirt am I wearing?
I'm not sure what I say. Words are breath.
Coral, okay. Anybody not see?
I didn't know.
Oh, should have put it on there, right? You guys remember the social media thing is to dress blue or is to dress gold,
Oh,
right? Okay. All right, so we gather sensory information from our environment all the time. Hot, cold, colors, sound, okay? Don't poke your neighbor yet, okay? Touch. Okay, no, not yet.
You say don't poke your neighbor.
Don't poke your neighbor yet, okay?
Touch.
So, we gather that information. You're going to gather that information through what we call sensory nerves or sensory neurons, okay? We have different things that connect everything else. Here's the other thing that I want us to we're gonna try to illustrate today, okay? 2 things. 1, put your arm back up over your head.
Go.
As that happens, watch your neighbor or watch the person in front of you. Arm down. Watch your neighbor, the person in front of you. Arm up. Do they move? Do they shift a little bit in where they're going? Think about I'm doing this. I'm moving. I'm trying to balance. So we need to do something else. I'm up here. If I do this, press it, right? What am I doing? As my leg goes out to one side, what happens?
The other side of your balances.
Counterbalance. Okay? Am I thinking about, I better counterbalance while I'm doing this? No. Sense, position, right? Motor, I move, I contract muscles, and I move to counterbalance. Arm up, right? As it goes up, we sense where we are in position, we begin and we counterbalance again. Okay? If I had something to throw at somebody, you do the same sorts of things. Okay? That's what we're going to talk about today. Sensory motor integration. You sense something from your environment, and then that informs muscle contraction. That informs how the nervous system tells muscles to contract. Okay? Now, I'm going to do it another way. A
Good girl.
special case of sensory motor integration. All right. Everybody sit, come back until right in front of the desk is sort of right underneath your knees. Nice and relaxed, nice and relaxed. Take a hand, okay? And we're going to karate chop right below your patella, okay? Right below your patella. Okay? What happens right there? That's called a reflex. Okay, that's the tendon tap reflex. Okay, why does that happen? You're relaxed, you don't mean to contract your muscle, and yet it just happens. Doesn't. Okay? It just happens. We'll talk about there are specialized muscle fibers that drive that. Okay. Okay, don't go back. We'll wander through this a little bit. Take about 10 minutes, and then we'll get on to talking about resistance training. Okay, so we have spent, for the most part, class up until now talking about both the central nervous system, so kind of brain, spinal cord, but as those things are connected over here through the peripheral system into the motor, sort of the motor side of things, what we would call the somatic, okay, the somatic side. This is alpha motor neurons, axons out to the neuromuscular junction, muscle contractions, connected to brain and spinal cord that drive and tell us when to do all of this, okay? Within the peripheral system, though, you have additional kinds of nerve endings and neurons, and they are what we call sensory neurons. I'll give you guys some examples of those in a few minutes, but you have nerve endings. Some of them are called type 3, some of them are called type 4, which denotes their size and if they have myelin or not, but they are going to be sensitive to pressure or touch, hot, cold, okay, light, different chemicals, hydrogen ions especially, okay, so acidity and electricity or anything else, basically anything that we can feel or experience is going to be the result of information brought in from the sensory side. It's going to come from the periphery back to the central nervous system, and then in specific brain areas, you turn that information into red or blue or hot or cold or gentle pressure versus getting squashed by a truck.
Over here.
Okay. That is going to be how the brain interprets all of these things. Okay. We'll do another fun exercise. How many of you have ever had a local anesthetic? Guess what a local anesthetic is? Right? You go to the dentist, they inject you with stuff, right? And then they drill into your tooth and you don't feel it. Okay. So when you get a local anesthetic, you're basically, what is happening is we are blocking the ability of these sensory nerves here either to depolarize and fire, or the ability of whatever once it's fired to get into the peripheral nervous system to get back to the brain, right? You're still getting the same input. You're just unable to transmit it to your brain so you don't feel it, right? They're still drilling into your tooth. All of that is to say. When you get a general anesthetic and they put you under, right, then they're actually blocking sort of how the brain is able to interpret all of these signals that are still getting generated, okay? All things like pain and hot and cold and light and all of these things are simply your brain interpreting physiological input from peripheral nerves, okay? So if again, you block or change that anywhere along the line, then you don't perceive things in that. Okay. All right. So let's talk about a few brain areas that are going to be important for integrating sensory information as well as some motor information as well. Okay. We're not going to go any deeper than this. This is not a class in motor control. It's not a class in neuroscience or anything else. All I want you guys to be in some ways aware of are sort of these four large areas of the brain. Okay. There's the cerebrum. There's the diencephalon, which is going to be where the thalamus and hypothalamus is going to be. There's the cerebellum, where the primary motor cortex is. And then there's the brainstem, which is going to be farther down, which really is going to be the place that controls some of our autonomic functions and things like, okay, respiration and cardiovascular responses. Okay, so you can also look at all of this if you want and look at things in purple. Here's the frontal lobe. Temporal lobe, right, is over here in blue on the side. Parietal is up there in green, and then the occipital is going to be sort of in the back. These are the areas of the cerebrum. The cerebellum is this area right here, right? You guys probably have had more of this than I have, and you're going to have sort of brainstem, right, pons, medulla, things coming out here on the bottom down into the spinal cord, and then kind of right in the middle here, right? That's where the diencephalon is. That's where the thalamus and the hypothalamus, which are going to be really, really important for integrating sensory information, and then hypothalamic control of body temperature and breathing and a whole bunch of different kind of hormone release and those kinds of things is going to be from in there. Okay. Y'all seen all of this before, I assume, either in anatomy or in human phys or in general psych or something, right? So all I want you to know are the very, very basics of what I have that's going to be up here. Okay. So if we look at things in the cerebrum, the reason that I kind of break it out, frontal lobe, so stuff here, this is primary motor cortex is in the very front, okay? And this is where intellect and memory and things are going to be housed. Temporal lobes on the side. There's lots of things that go on, but if you're thinking of sensory information, it's stuff that we hear, auditory information, okay? Parietal up here is other types of sensory input, position, heat, cold, things like that. And then occipital in the very, very back, that's where vision is, okay? If you reach over, don't do this and smack your neighbor right in the back. Usually you'll blink your eyes and you'll sort of lose vision for like a millisecond or something, because when you tap the occipital lobe, that can be a thing that happens. Okay. All right. So again, different regions of the brain control different things. This is why when you have a stroke or something like that, you can have these differential effects on things, because depending upon where we don't get blood flow or we get neuron death and things, it will control sort of that area on the opposite side. It will control sort of what we're going to lose or not lose on this. Okay. So that's how that stuff is going to work. Okay. So I'm going to mention a little bit of this, even though we've kind of done a bunch of it already in talking about kind of the motor side of the system. So generally when we talk about the peripheral nervous system, so sort of things downstream basically of the spinal cord, you've got 12 cranial nerves that are going to connect to the brain. are going to come out or project out from the spinal cord. And we basically break this peripheral system into the sensory division and the motor division. And then kind of within the motor division, we're going to talk about there may be autonomic system input, okay, as well as the somatic or voluntary motor control type of thing. We've spent a lot of time talking about the somatic system already. Alpha motor neurons, axons, out to muscles, voluntary control of force and muscle contractions. We will cover the autonomic part in great detail in the cardiovascular system and in ventilation and respiration for the pulmonary system side of things, as well as how we control sweating and body temperature and a bunch of things there. Okay. These things tend to signal from inside near the spinal cord out, right? Signal brain, spinal cord out to tissue. That is called an efferent signal carried by efferent nervous system fibers or axons or neurons or however you want to break it up. Okay. The sensory division does things in the opposite way. Okay. Everybody touch your arm lightly, just touch. Okay. Feel yourself touching your arm, yes. Okay. What is happening is you touch on the arm, you activate these sensory nerves and these sensory nerve fibers. They signal through what are called afferent or afferent muscle fibers, or afferent nerve fibers. Sorry, gosh, I don't know what I'm doing here. And they signal from out in the periphery back to the spinal cord and then up to the brain. Okay. I showed you guys a picture of this. We didn't talk about it hardly at all. We will do a little bit more is at a given site in the body. Okay. At a given site. So like forearm here. Okay. I touch my forearm. Afferent information comes back. It travels up into sort of the brain. It's going to reach in the spinal cord at relatively the same level as where the motor neurons are. It's just going to come in on the opposite side of the spinal cord. So what happens is afferent information comes back and it would arrive, let's just say at C6. Okay. The alpha motor neurons that would control my forearm muscles are also going to sit at C6. Okay. But they're just going to come in on different sides of the spinal cord, but they're very close to each other. By being very close, they can talk to each other. So I feel this hurts. Okay. Then that information is going to do certain things and may alter the excitability of the motor neurons, right, to my forearm muscles that are very sitting there in the spinal cord very close. And then I may want to try to pull my arm away from whatever it is that is painful or whatever it is that is hurting. Touch something hot and pull away. Okay. Some of that is a reflex. Other parts of it is driven by we get it up into the brain, decide what it is, and then make a conscious decision as we come down to do something else. Okay. That is this idea of sensory motor integration. Okay. But it's driven by some sort of sensory information sent back into the brain or the spinal cord via afferent fibers, and then we're going to get some corresponding motor firing that's either going to move away, change posture, whatever it's going to be in response. You have sensory input from almost every tissue in your body, except your heart, which I find always to be super ironic, right? Internal organs, right? You have stomachache? Okay. Anybody ever had an appendicitis? You have? Not very fun, quite painful, right? Okay, internal organs. You have things in connective tissue, okay? In connective tissue. Tendons, ligaments, very important for proprioception or deciding where you are in space. There's a tremendous amount of sensory neurons around blood vessels, okay? Around blood vessels. You have a tremendous amount in your skin, okay? Are there places on your skin that are more sensitive than others? Yeah, right? Fingertips, more so than some other places, right? If I pinch you on your face, I don't have to pinch nearly as hard as if I pinch like down on your heel or something, right? So we have these skin receptors. We also have things in muscle. Okay, we also have things in muscle. Different organs, different places and locations on your skin and in your body have different levels of sensitivity to different types of input based upon the density of nervous system innervation in those areas. Okay, you have more nerves that sense touch and pressure and hot and cold and things on your face than you do on your heel. Okay, more in the tips of your fingers, right, than you do, let's just say, on your forearm. And that helps us in those particular areas have certain functions, right? We can sense touch and pressure and things. We want to keep things away from our face that are going to hurt, and therefore it's less of an issue at the heel. Okay? Here are the individual types of receptors. Okay? We have what are called mechanoreceptors. Mechanoreceptors respond to a mechanical input or a mechanical sort of deformation of a tissue. That's what touch is. You press, it mechanically moves the skin or the muscle underneath or the connective tissue, right? Touch, pressure, stretch. All of these things activate mechanoreceptors. Okay? When I bend over like so, yep, I can feel stretch in my hamstrings. I bend my knees, there's less. I sense all of that because of mechanical deformation in muscle and ligaments and tendons. That's a mechanoreceptor. Thermoreceptors are just what you think. They sense hot, they sense cold. Okay? They sense hot and cold. They're what we call chemoreceptors that are very sensitive to a host of different biochemicals. Okay? And by biochemicals, that might mean potassium, okay, hydrogen, lactate, ADP, inorganic phosphate, you name it. Okay? You've got some for all of them. We have what are called photoreceptors that sense light. Okay. And then we have, and this is, I probably should move these things around, but you have what are called nociceptors that sense pain. And to be really, really, really clear, you have nociceptors, like you have mechanical nociceptors, you have thermal nociceptors, you have chemical nociceptors, you have photonociceptors, and then you have some that aren't going to be all of that. So if you get enough touch, enough pressure, enough hot, enough cold, then it is sensed as painful or not. Okay, but those are the types of receptors that we have. Anybody ever exercise and you feel like your muscles are burning? If you haven't, you need to work out harder. Okay, if you feel like that, what you are experiencing is activation of a chemoreceptor that senses hydrogen. Okay, you work out at a pretty high rate. Metabolically, we make lactic acid that dissociates into lactate and hydrogen. The hydrogen binds to a chemoreceptor, and that's why it feels like your muscles are burning. Okay, you change the pH inside of that muscle. You stop, we clear all of that out, it goes right away. Okay, it goes right away. So all of these things can be experienced kind of all at the same time. And they may have, certain effects on our ability to exercise or move or things of that nature. Okay. So we're going to talk about a couple of very specific muscle and joint sensors. Okay. We need to have an ability to adjust force production moment to moment in order to prevent injury. Okay. If I hold my can of Diet Mountain Dew out like this, right? I can sense if it's moving up and down. I can sense as I begin to fatigue that I'm not getting enough force and it's moving its place and position and those things, and I can initiate a stronger or more forceful muscle contraction because of all of that. Or there are other instances where you generate so much force that actually you get inhibition and it shuts things down. Okay, so we'll talk about how are we going to get these things. You have inside your muscles something called a muscle spindle. You have something called a Golgi tendon organ. You have what we call kinesthetic receptors, which sense joint angles and position. And then you have these random kind of what we call free nerve endings that are going to sense all the stuff we talked about on the slide before. Pressure, temperature, chemical. We're going to focus very much on these first two, okay? A muscle spindle and a Golgi tendon organ. Okay. So a muscle spindle is a special type of muscle fiber. And its one job is to sense length, okay? It's a mechanoreceptor, so it's activated by stretch or lack thereof, and it senses the length of the muscle, right? It is a collection of these very, very small, what we call mini fibers that are termed intrafusal muscle fibers. So you open a muscle up and a Golgi and a muscle spindle looks a lot like, from the naked eye, a lot like a regular muscle fiber. Okay, but when you look microscopically, it's going to be a little bit different. It's called an intrafusal fiber. Regular muscle fibers are actually called extrafusal fibers. Okay, you have many, many of these at regular intervals in a muscle. Okay, and what makes them unique is that muscle spindles have sensory innervation and motor innervation. I'll talk about kind of how that works in just a second, okay? But what generally tends to happen is as you stretch a muscle, okay? As you stretch a muscle, the muscle spindle senses that it's getting stretched, okay? That is that sensory information. It senses stretch. When it senses stretch, it activates a reflex, okay? You guys know what a reflex is? What makes a reflex different than sort of a regular kind of muscle contraction or something? No. It's not voluntary. Why is it not voluntary? It does not go to the brain. Okay? A reflex is like a pre-programmed pattern of nervous system activation that does not require a signal to reach the brain in order for it to initiate. Okay. What we did with the tendon tap reflex, when you guys sat and the karate chops right below your patella tendon, you pulled the tendon. As you squished the tendon stretched, the tendon's connected to the muscle stretches, it activates those spindles, and then the spindle, when that sensory information that the muscle is lengthening reaches the spinal cord, it immediately tells the alpha motor neuron of that muscle contract. You don't need the brain, you don't, that actually gets messed up if you get voluntary control there. It just says fire, 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 okay? We are stretching, this could be catastrophically bad, give us more force, okay? Give us more force. Overstretch is bad. It will rip a muscle in half, it will rip a tendon off of the bone and these kinds of things, okay? So when you activate the spindles, it tells that muscle where the spindle exists to try to contract and generate more force. So it will stop stretching. Okay? So that's what goes on there. So this is going to kind of walk us through this, okay? We activate the spindle back to the spinal cord. So because it synapses directly onto the alpha motor neurons of the muscle where the spindle exists, we call that a homonymous motor neuron, okay? Spindle in my quads it will signal back to the spinal cord and directly turn on the alpha motor neurons of my quad. That's what makes it a homonymous motor neuron. So spindle activation excites or leads to a depolarization of the homonymous motor neuron. Okay. It also, okay, it will also inhibit the antagonist muscle. So you activate your quad, it was going to try to get us more force from our quad and also turn off the hamstring. Okay, will also turn off the hamstring. So that will be good. The idea then is more force, less stretch, no catastrophic ripping of my muscle in half. Okay. Now, we're not going to get into kind of the hows and whys of it, but I told you guys that the spindles also have motor innervation. So one of the things that happens is as you stretch a muscle, it senses that stretch, it tries to adjust force, but as the spindle gets stretched out itself, then it has a motor innervation from what's called a gamma motor neuron. And it will tell the spindle to start trying to change its own length. And as it changes its length, it will change its sensitivity. So you can basically make a spindle more or less sensitive to stretch by altering those things around. And so you can actually train your muscle spindles to be more or less active. You can do some wild, crazy things by doing all of that. Okay. Not something that we have to know that I'm going to ask you a question about. Okay. Now, we call a Golgi tendon a muscle receptor. Technically, the Golgi tendon is located in the tendon that connects to a certain muscle. Okay. So the Golgi tendon organ for my quads is located in the patella tendon. Okay. And what it senses, and this always seems weird and backwards to me, but the GTO senses force. Okay. Force. Not length, force. So you have these nerve endings that are woven into all of the collagen fibers in that tendon. As the muscle generates force, that tendon stretches, it squeezes those fibers that are woven between the collagen molecules, and then activates the Golgi tendon organ. Okay? The purpose of the Golgi tendon is to keep you from generating so much force, okay, that you essentially rip the muscle and the tendon apart. It's protective of these massive levels of force production. Okay. So the Golgi tendon, it synapses also on the homonymous motor neuron. So GTOs in the patella tendon signal to alpha motor neurons in my quads. But they do the opposite of the spindle. Okay. GTOs inhibit the alpha motor neurons of the homonymous motor neurons of that muscle. And they activate the antagonist muscle. Right? So I'm doing a huge amount of force on the knee extension. I activate the GTO. It says turn off quad, turn on hamstring, lower that muscle, lower that weight down. Let it go. Okay? Let it go. So it does the opposite. Okay? Spindles protect from overstretch. Golgi tendons protect from too much force. They protect from too much force. Both of them activate reflexes and things that do not have to go to the brain. Okay. So I've told you guys sort of stretch and tendon tap reflex. There's another one called the flexor withdrawal. You ever touch something hot? Okay. This is this idea of how we change positions. I touch something hot with my right arm. As I pull away, as I flex to withdraw, I extend on the opposite side so I don't fall down. Okay, so that's the flexor withdrawal thing. Olivia.
Is the Golgi tendon organ also a mechanical?
Mm-hmm. It is a mechanoreceptor. It is a mechanoreceptor. Okay, so those are reflexes. We're not going to get into anything any more than kind of whatever is there. Okay. All right, we're gonna not cover any more of the slides than this. The back, like 3 or 4 slides, I'm not gonna ask you guys any questions about. We're gonna save the sympathetic nervous system stuff until we get into the cardiovascular system. Okay? So the overall idea of sensory motor integration is very simple. You sense something, that signal is interpreted either in the spinal cord or the brain, and then it evokes something where you change your motor output after the fact. Okay? Change your motor output. All sorts of wild, crazy things that go on. If you are exercising and you're running and the muscles in your legs are beginning to burn, what is your most likely thing that you're going to want to have? You're going to want to do? Stop. That's the sensory motor integration. You want to stop because you're sensing that this is burning and maybe it's painful, and the brain intuitively knows this is not great. So then what it does is that leads to a phenomenon called hyperpolarization. So it makes it more difficult for the motor neurons to depolarize that lead to those muscles. So you have to send a bigger signal from the motor cortex to continue to get those same motor neurons to turn on and generate that same force production. You perceive that then as being more effortful and more difficult, in addition to the fact that it hurts. And at some point then, it becomes too much. You cannot turn on all of those muscles anymore, and you slow down or you stop. Okay? That is this idea of sensory motor integration. The single best thing that you can do to exercise better is what I have in my hand right here. Okay, what's caffeine? Legally, it's caffeine. That's the best thing that we can do. Caffeine blunts some of the sensory information. Okay. Caffeine is a fabulous pain reliever. Okay. Especially for exercise-related muscle pain. It blunts that. It also makes the motor system more excited. So it kind of hits it from both directions. So it can stave off some of that feelings of pain and effort and things during exercise, and it also maintains excitability on the motor side. So the sensory information has less of an effect. That's why caffeine is good. Another alternative that we can do, right, is I can just inject you adrenaline. Sure. I was going to suggest something like xylocaine or something like it. I can give you a local anesthetic. The problem is when you give a local anesthetic is they're very non-specific. So you lose the sensory information, but you also tend to lose the ability, the motor side, to be able to activate things down there as well. It just blocks all sort of sodium channel function in those cases, right? So you get that in your mouth, right? You can't feel it, but you get a little droop, right? You can't chew, you can't, those kinds of things. That happens. You guys heard of something called fentanyl? You guys know what fentanyl is? It's an opioid, right? So you can, and people have done this during research, and it's fascinating. Now, of course, our IRB will never let us do it because I'm not an anesthesiologist, which is kind of sad. But things that my anxiety is not up for is this person is asleep, you put them under, if you get the drugs on, they're gonna die right now. I'm out, not for me. Anyway, good anesthesiologists, they come and they inject fentanyl onto the dorsal side of the spinal cord. This is what an epidural that women get when they're pregnant, or something like that. Okay, an epidural injection of fentanyl, you can just put it in far enough that it only goes on the ventral side, so you can prevent sensory information. You can block sensory information while maintaining motor information. You feel phenomenal, apparently, okay, or so I have been told. And you ask a person to go and exercise, and they just tear ass out of the gates. And they can't perceive the fact that they're accumulating lactic acid, that they're accumulating high muscle forces and all of these things. And they go out really fast and then they can't pace themselves at all. And they get tired and they fatigue and they stop. So this lack of sensory information actually inhibits and is bad for exercise performance because you have to be able to get some to be able to integrate these things to do whatever it is that we're doing. It's fascinating. And then apparently you feel terrible the next day after you've had the fentanyl injection. So headaches, all kinds of things in the midst of all of this. If anybody's ever had surgery, some of you had a nerve block, that's what this is. That's what the fentanyl is. It's a nerve block. So, okay, we're going to stop here with this. Okay, we're going to stop here. Questions about that? We'll have our quiz on very, very brief sensory motor stuff. First thing in class on Wednesday. Okay, first thing in class on Wednesday. All right, stop sharing. Maybe. Going to stop recording.